Hello there. Let's go over the CSM 61B Fall 2017 worksheet for binary trees. So mentoring 8. Let's get started. So for this worksheet, we're going to be covering binary trees, and as we all know, binary trees have a root node, and then within each node we have the value itself, and then a pointer to the left node and a pointer to the right node. Since these are binary trees, each node only has at most 2 children. So for 1.1, we're told to define height. So pass in the tree, and then you should be able to find the height of the entire thing. So let's go and try to write this. So for part 1, given this, we know that, normally when I try to approach tree problems, I first figure out what the recursive call would return if you applied it to the children. So let's say we applied height on everything on the left. That should just give us 1. And then let's return the height of everything on the right. That should give us 2. So, and we know the entire height of this entire tree should be 3, right? How did we even get that? Well, we got it from taking the maximum heights of either children and then adding 1. So let's write that as our recursive case. So we have return 1 plus math.max, the height of the left node, node.left, and the height of the right node, so node.right. Cool. So what should the base case be? Well, in this case, it just tells us right here, the height of the leaf node should be 0, right? So if we're at a leaf node, our recursive call, as it is going to go into the children. So it's going to go into a child and then realize that it's null. So if a node is null, then we should return 0, right? No. Actually, since the height of the leaf should be 0, when we're right here, 1 level below, we should be returning a -1. That's because, remember, for a recursive case, we're adding a +1 at the end. So instead of putting down a -1, instead of putting down a 0, we should be putting down -1. Yeah. So what's the runtime of height? So when we're calculating this, taking the height of the thing on the left, well, that just gives us, it ends up checking out how many nodes? Just the exact number of nodes that we ended up putting in. So, and then it does the same thing on the left, and then we finally add in a +1. Overall, we end up exploring every single node exactly once. So in the end, our total runtime is going to be O of n. N being the number of nodes. So it's linear time, and that's because if we add 1 more node, we end up having to explore one more node in the end. So in the end, it's going to be linear time. Now let's talk about 1.2, is balanced. So define procedure is balanced, which takes in a node and outputs whether or not it's balanced. And the key statement here is that a tree is balanced if the left and right branches differ in height by at most 1, and the branches themselves are balanced. So actually, you can pretty much just take this line and turn it into code. I love it when they usually give us definitions like this, because usually it's just a straight translation to solve the problem. So if the left and right branches differ in height by at most 1, so if the height of the left branch and the height of the right branch is at most 1, or the difference between the two is at most 1. Oops. And it's true what a tree is balanced if the heights are the difference between heights are most 1, and they themselves are balanced. So all we had to do at this point is check whether or not they are balanced. So now we just have to return, oh, but since this is a recursive method and we are writing as balanced, this is where our recursive call is going to be. So node.left and is balanced, node.right. What about the what about the base case? So maybe some possible base cases if we have no nodes or we only have one node. So, but let's figure out if we had to choose between 0 nodes and 1 node. So if we had 1 node, we would go in, find the height. The height is going to be -1 minus -1, da da da. So it wouldn't even go here. So we should just like write a base case for if the node is null. And then for this, we could just return true, because if you have nothing, then, well, it definitely is balanced. And then we could change this to an else if. Here you go. Now let's talk about the runtime of this. So this one can be a little confusing, but basically I would like to talk about how the runtime of this changes depending on the shape of the tree. So let's say, for example, we have a tree that looks something like this. So it's really long. It only has children on the left. So it's a spindly tree. Da da da. Spindly, spindly. I might have spelled that wrong. Spindly. Yeah, spindly. That is correct. Spindly tree. So we only have children on the left. What do you think the runtime is on this? Time on a spindly tree? Here, I'm going to comment this. So what we have right now, what will happen is that it will go past the if case and it goes straight into our recursive case. Else if the height, so it will first check the height of everything on the left. So we have a runtime of n, so it'll check everything on the left, and then it'll check, well, the nothing on the right, and then it'll realize right away that it is not that the difference is greater than 1. So, we should return false at this. Notice right away that the difference is greater than 1, so we'll go straight into the false case. And this is actually the best case scenario. Because all we do is we run height on both the left and the right once each, respectively. And since we know that height runtime is O of n, and we end up basically doing, and then everything is on the left, so we know that the final runtime for this is going to be O of n for the best case scenario when we're running is balanced on a spindly tree. What's the worst case scenario? So let's talk about a bushy tree. So I hope it's kind of clear what it's supposed to be like. So we have one node here, has 2 children, and then each node has 2 children, and each node has 2 children. So it's very fat, very bushy. So what's the runtime on a bushy tree? This is going to be, so now things are a little interesting. So we definitely know that the height is going to, the runtime of height is n. So at the very, very top, we end up doing 2 height calls, right? So, so we do height. So if the original size is n right here, on this level, we're going to run a height call on n plus 2 nodes and a height call on n plus 2 nodes, n over 2 nodes. So this is node.left and this is node.right. And we know that it divides by 2 or it's approximately divided by, it's approximately divided by 2 because we're leaving out this 1 at the top. And then they're the same and they're even. And then the height values are going to be like this. And the total runtime just for this level, it's going to be O of n, because since height's runtime is O of n, if you run height on something that size n over 2, this total runtime is going to be n over 2. And since we're doing it twice, it's going to be O of n just for this level. On this level, we're going to end up doing 2 more height calls. So this one, this node right here, because we want to go into this node, the size of this problem here is going to be n over 4. So height n over 4 plus height n over 4. So these are 2 nodes here. And then we also do the same thing for these 2 nodes here. So the runtime for this level is once again 4 times O of n over 4. So, which we know for sure is O of n. And so on and so forth. So this level is going to be O of n. So in the end, since we know that there are approximately log n levels, and each level we have a runtime of n, we know that our final runtime is going to be n log n for a bushy tree. And then, is this the worst possible, is this the worst case? Is this the worst case? The answer is yes. Because if you end up having anything less bushy, each of these height calls will be a smaller value. So it's going to be asymptotically be less than n on each level, or not for all levels. So actually, for a bushy tree, we have the worst case runtime. Because if you're less bushy, runtime is to be less. So runtime on the bushy tree is n log n. Alrighty. Alright, so let's talk about 2.1. So we're talking about binary search trees right now. For 2.1, we are told to implement from sorted array for binary search trees. Given a sorted integer array, effectively construct a balanced binary search tree containing every element of the array. So the BST class is right here, and then we have this method right here. The first thing that happens is that we make a new BST. We set the root to be the result of applying from sorted array onto this currently empty BST, and then in the end we return it. So notice how from sorted array returns a node. What we should be doing is we're going to be making this BST, and then we should be returning the final thing. And if at the end we're going to use this and return that BST. So the approach for this one is something like this. Let's say we know that array is 4, 5, 6, 7. It's sorted. And so basically how we're going to do it is, the first thing we do is that we pick out the middle element, so 4. And then basically we recursively run from sorted array on everything to the left and everything to the right. And then we set the child of this, set the left child of 4 to be the result of applying from sorted array to everything on the left, and set the child, the right child of 4, to be the result of applying from sorted array on everything on the right. So 4 is out, and then we apply, and then what's next is that we pull down these 3 values. We run from sorted array on these. So then 2 is now taken out. And then because of that, it goes down even further. So then 1 is taken out. because it's the middle of the whatever is left, and then finally 3 is taken out. My indices, okay. And then so on and so forth. So we have 6 taken here. We have 5 taken, 5. And then finally we have 7. And then now we have a balanced BST where everything on the left is less than the current node, and then everything on the right is greater than the current node. So let's write this. So let's start by determining what the middle value is. So let's say int middle is going to be, okay, so a lot of people are probably going to do something like upper plus lower divided by 2. This works. However, if both upper and lower are really, really big, you might run into some overflow errors. So to get around that, we can say lower plus upper minus lower divided by 2. The problem before is that when we had upper plus lower divided by 2, if the sum of upper and lower is greater than the max integer value, we're gonna have some errors. This will lead to errors and sadness. Same thing if so if this happens, Java's gonna crash and no one's gonna be happy. But if you do this, you can definitely get around that. So yeah, moving on. We're gonna set this middle node to be, we're gonna make a new one, a new node. And then at the very end, we're just gonna be returning this. Now let's set the children of this node. So mid.value value is just going to be values.middle. Values is the given array that we had earlier. Mid.left is going to be the result of calling from sorted array from everything from its current lower bound, so lower, and then to middle minus 1. So remember, middle is the index of middle, even. And then semicolon. Mid.right is going to be something similar from values. And then we want everything right on the right side after middle. So we have middle plus 1 and then upper. So then this should take care of doing most of the work for getting a binary tree from a sorted array. Now we have to consider some base cases. So let's say we had something like 5 and 6. This should be giving us the tree 5 and 6, right? So how do we ensure that happens? So what we have right now, middle is going to return, this is going to say middle is at index 0, and then so it's going to make the node 5, which makes sense. And then now what's going to happen is that our code is going to run from sorted array from 0 to middle minus 1, so 0, 0. So we have 5, and then we're going to have from sorted array 0, negative 1 as the left child, and then we're going to have from sorted array 1, 1 as the right child. Obviously, when this happens, we want it to return nothing. So that's the case when lower is greater than upper. So if lower is greater than upper, we just want to return null. So this ends up returning nothing, and then this should return 6 for us. And that's it. This should be the code required for part 2, 2.1 from sorted array. All right, now let's talk about part 3 successor. But before we do that, let's talk about the following traversals. So pre-order, in order, and post order. So all of these are def first traversals, which means that we visit deep nodes before shallow ones, and then level order traversals, we'll talk about this one later. So talking about def first traversals, all 3 of these have, I think they're actually pretty well named. For when we're traversing a tree, these dictate the order that we visit nodes. So for pre-order, what we do is that we visit the current node. Current node before we visit the branches. So current node before we visit left, and then visit right. So the first thing that we do, we traverse the first node, and then we check out everything on the left, and then we check out everything on the right. So, but when we go into the left, the first thing we do is that we check the current node before checking everything on the left, and so on and so forth. So we're going to have some better examples of this in a few. Let's go over the rest of these. In order is kind of what you expect it to be. So you have left, and then current, and then right. It's in order. And when we run this on this tree, it's going to give us a really interesting effect in just a few. We'll show that later. And finally, post order, we do left and then right, and then finally we do the current node. So we end up searching current after everything. So for all of these, the whatever X order thing, X refers to the current node. Or perhaps not current node, but just like the node that you're currently traversing. So current left right, left current right, current right, and then left right current. So if you haven't heard of the dotted line trick, I'm going to show you it now. So what the dotted line trick is, basically you draw this kind of dotted line around the edge of your tree. Or I guess it doesn't have a dotted line, but a line of some sort. And then you draw a dot, this kind of dot, depending on what kind of traversal you're doing. So if you're doing a pre-order, you draw a dot on everything on the left. If you're doing an in-order traversal, just at the center, at the bottom. And then if you're doing a post-order, just everything on the right. And then you just kind of like follow the line. And then whenever you pass the dot, that's that's the node that you want to add to your list. You would have traversed that node when you passed by. So the first thing is F, B, A, D, C, and then E, G, I, H. So the pre-order traversal of this tree is going to be exactly the letters I just read out, B, F, D, A, C, E, G, I, H. And then the trick works for everything. So for in order, we do A, B, C, D, E, F, G, H, I. And then for post order, we do A, C, E, D, B, H, I, G, F. So let's kind of like apply this trick to this tree, 1, 2, 7, 5, 9, 3, 4. We're going to find it kind of hard to draw, so I'm just kind of we're going to mentally do it and hope that we end up with the correct traversal. So with pre-order, that's everything to the left. Yeah. So first thing we should hit is 1, 2, 5, 9, 2, 5, 9, 7, 3, 4. And that should be it. Let's check it out. Correct. Now let's do in order. So remember the dot is at the bottom for this one. So we're going to have 5 to 9, 5 to 9, 1. Mm, 7, 3, 4. Yeah. Wait, 7, 4, 3. 7, 4. Yeah, 7, 4, 3. I guess it isn't really clear for this case. Oh yeah, no, right. It's correct. So if there were something on the right, then the dot would be right between the branches. So yeah, that makes sense. So yeah, it should be 7, 4, 3. And then finally for post order, we have 5, 9, 2, 4, 3, 7, and then 1. So just showing that I'm not crazy. Yeah. Oops. Now for level order, all we do is we just kind of read it row by row. So first row is 1. Next we do 2, 7. Then 5, 9, 3. And then finally just 4. So that's just level order. We just kind of go by level. Finally, let's talk about writing successor. So given a node in a binary search tree with parent pointers, this part is really, really important. It's pretty much if you're given a node in a binary search tree, so any of these, if you don't have access to the parent, you won't be able to solve this problem. And so we're told to implement successor, which returns the next node in an in-order traversal to BST. So remember the in-order traversal for this one is going to be 5 to 9, 1, 7, 4, 3. There's no successor, return null. So we have 3 cases here. For most of these, let's talk about the easiest case first. So let's say we're at 2. We know that the successor is going to be 9 because at that point we have already visited the current, and then now we have to visit the right node. And then this node, there's nothing on the left, so we can just visit the current, and then there's nothing on the right, so we can just return 9. So there are 3 cases. So if there's a right node, go right, and if it's a leaf, then pick that. What about the case if we go right and then there's still stuff on the left? So if, say example, we're at 7, we go right. So you go right, and then since we're doing an in-order traversal, we had to keep exploring everything on the left before we explore the thing that's in the center. So in this case, we go right and then keep going down left. So if there's a right node, yeah, there's two options. We can go right, and if there's a left node, go all the way left. It's invisible. But then actually, we can just simplify all this and just be go right and go all the way left while you can. So that would actually cover both of these cases. Now, if there's a case where there's no right node, we don't do anything with the left because we are kind of, since we're currently exploring the current node, we kind of going to assume that everything on the left is already explored. So there's nothing on the right. Let's say we're at 9. The next node we should be returning is 1, right? So what we should be doing is that we should keep going up until we can go right again. So we keep going up. So for at 9, we go back to 2. And for 2, we go back up to 1. We keep going up until this thing on the right is something that we haven't seen before yet. So it's going to be 7. So if there's no right node, go up until the node on the right isn't the branch we went up. So I guess there are two cases here. So let's write this. Oh no, my tree. Whatever. It's okay.